2.2. We need to learn how to divide polynomials. And the way I learned to divide polynomials was an awful, terrible, horrible mess. And I'm not going to make you learn how I did it. Some teachers still teach this way, but I don't like it. Let's say I had x squared minus 6x plus 5, and I multiplied that by x plus 2. Okay? And write this down because it's going to look really weird at first, and once you get the hang of it, it's pretty slick. But it's so much better than the way I learned it. I'm going to multiply that in a 3 by 2 multiplication box. So I'll put x plus 2 on the left and x squared minus 6x plus 5 on top. When we multiply that out, I get x to the third minus 6x squared plus 5x, and then 2x squared minus 12x plus 10. Okay, once you have the box filled out, just stop for a second, because I need to point some things out. So, look at how the box is arranged. X to the third, x squared, x. We go down to the next row, x squared, x constant. Okay? That only happened because these are in order. And this won't apply today, I don't think, but we didn't skip any variables. We didn't go from an x squared to a constant. Okay, that's going to be important later. And then notice my like terms occur on the diagonals. X to the third has no like term. It's by itself. But the x squareds are on the same diagonal. Negative 4x squared. And then my x's are on the same diagonal. Minus 7x plus 10. Okay, that's like 8th grade stuff, right? So, if A times B is equal to C, then A divided by C should be B. Meaning, oh wait, I did it wrong. Boy, sorry. If A times B equals C, then C divided by B is equal to A. Does that make more sense? Sorry, guys. So, if A times B equals C, then I should be able to do C divided by B is equal to A. So, if I have x to the third, oh, now I can't see it, minus 4x squared minus 7x plus 10, and I divide it by x plus 2, I should get that quadratic that I had at the beginning. Okay? But how do you divide polynomials? Well, if this was divide by 3, then I would just divide each individual piece by 3. But I am dividing by x plus 2, which are counted as their own factor. Okay? We are going to use the box and go backwards. Now, there is a way using long division that you can do it, but it's so easy to make a mistake, and it's so easy to miss something. But the box doesn't allow you to forget anything. So here's what we do. We start a box that has that many rows. So I put an X and a 2, but I don't know how long the box is going to be. And actually, the length of the box is going to depend on what happens when we do the division. Sometimes boxes are longer than others just because of what happens. Okay, So we section off one column, and I put this in the top square. X to the third. Okay. Now, what would go here? Something times x equaled x to the third, x squared. If that's an x squared, what goes here? 2x squared. Does everybody follow? Oh, I forgot the squared. Okay, now we ask ourselves, did I use the entire numerator? Not yet. The only one I've used is the x to the third. How do I use negative 4x squared? Well, I need another column, so I add a column. Should I put negative 4x squared right there? No, because it's on the diagonal. So this square and this square need to create that. I already have 2x squared, and I need to get to negative 4x squared, so I need to subtract 6x squared. Oh, negative, thank you. Do you guys follow that? Now, what goes here? Something times x is negative 6x squared, so it'd be negative 6x, and that allows me to fill this in, which is negative 12x. Have I used my entire numerator? Not yet. So I add a column. I need a negative 7, and I have a negative 12. What should I do? Add positive 5x. So 5x, and now this will be a 5, and 5 times 2 is 10, which matches this, so I'm done. Okay? This is the answer, which is exactly what we started with. Okay? What did I just do? Well, yeah, I just went in a huge circle. But let's imagine that we have this equation here, and I want to know, where does that graph cross the x-axis? Well, if I know that one of the roots is negative 2, I can remove the negative 2 from the graph and get an equation of what's left. So this touches the x-axis 3 times. If I know it touches at negative 2, I can do this division and remove one of its factors, and then I get this, which is x minus 5 and x plus 1. So this has 3 roots, negative 2, 5, and negative 1. And polynomial division allows us to remove roots one at a time. Or eventually we can remove them 2 at a time. Oh, negative 1, sorry. Yeah. There we go. Does that make you feel better? Okay, so let's oh, you really want to see it? Well, it's probably good that somebody shows it to you. So what was it? X plus 2 and x to the third. Help me out. Okay. So don't write this down. Don't ever do this. So how many times does x go into x to the third? X squared. Now we do this times this, and I get x to the third, and I do this times this, which is 5x squared. And then we have to put those in the correct columns. And sometimes they're next to each other, and sometimes they're not. So you put them in the correct column, and then you have to subtract, so you change the signs, and that goes away, and now I get negative 9x squared minus 7x plus 10, and then you do it again. But there are so many steps in there, and if this has 3 or 4 terms, then this is going to have like 8 terms, and sometimes it will be this one, and sometimes it will be that one, and it's a mess. It's a horrible mess, which I recommend you never, ever, ever do. Okay. So, what if I had so, I put x plus 1 on the left. Oh, shoot. Hold on a second. That's bad. We don't want to do that yet. There we go. So I put x plus 1 on the left. And I put the first one in its place to begin with. X to the 4th. What goes up here? X to the 3rd, and then I do this times this is x to the 3rd. Did I use them all? No. I'm done with this one. So now I move on to the next one. I add a column. This and this have to add up to be negative 1. How many do I need? Negative 2, x to the 3rd. Does everybody follow? Where'd you get lost? So all of my x to the 3rds are in this row. So those two have to add to be that. And I don't have any flexibility with this one. That one has to be 1 x to the 3rd, but I do get to choose the second one. And I just choose it to match. Now that I have that number, I can put negative 2x squared, and then this becomes negative 2x squared. Am I done? No. So I add a column. This one and this one need to make negative 6. So I subtract 4. X squared, sorry. Is everybody okay with that? Don't let me go on if you're confused. So this, I removed an x. So when I get to this step, I need to pull out an x. So I remove an x, and I'm left with negative 4x. And once I have that number, I can create this one, which is negative 4x. Did I use up all of my numerator? Not yet. So add a column. Okay. I have negative 4. I want positive 2, so what should go here? 6x. And then I yank out that x, and I get plus 6. And 6 times 1 is 6. Uh-oh. I've got a problem. Any idea what that means? No? What's the problem? What do you notice is wrong with this? It didn't work. Right? So I took care of the 2x, that's good. But what about this? My last number is a 6, and I needed my last number to be a 3. What does that mean? What's that? Well, I can't. It's not a bounce. In fact, it means that x plus 1 did not work. right? This equation is made up of 4 factors, right? And I was hoping that x plus 1 would match one of them. But it didn't. Does that ever happen in division? Sure. If I have 24 and I divide it by 3, I get 8. But if I have 25 and I divide it by 3, what do I get? I get a decimal. Well, we're not going to do polynomial decimals. So remember back to when you learned division. And you did long division. And you ended up with 8. And then what did you say? Remainder 1. Which is the dumbest thing ever. Think about it. I have a 25-foot rope. I want you to divide it into 3 equal pieces. And Jensen comes back and he says, great. Here are 3 8-foot ropes and a 1-foot rope. How well did Jensen do? Bad idea. Right? That doesn't make any sense. 8 remainder 1? All right. So what would be the correct way to do that? Well, let's not use decimals. So if Jensen wanted to do it correctly, he would think ahead, which is hard for Jorgensen, but so if he thought ahead, he's like, okay, wait a minute. I know I'm going to have 8 full feet. And then what should he do with that last 1 foot? Divide it into 3 pieces and put it with the other ropes, which means he has to cut them 8 and 1/3. Does that make sense? Right. So he needs to think ahead and do the cutting correctly the first time. Well, doesn't this really just mean that? 8 plus 1/3? Okay. So let's go back to our polynomials. We hoped, ideally, one of these is an x plus 1. Whoa, that was bad. Hopefully one of these is x plus 1. If it is, then we can just cancel it and I'll end up with an x to the 3rd equation, right? But most of the time that's not going to happen, right? If you just picked a number and divided it by a random number, what's the chance you have no remainder? Probably pretty small, right? It doesn't happen very often. So, how do we deal with the remainder? Well, it's a little bit weird. So we ask ourselves, did we get that number? No. So we add a column, just like we did before. When we finished this one, to get that number, we added a column. To get this number, we added a column. So I add a column. This number and this number need to add up to be -3. So what goes here? -9. Okay, now pay close attention to this because it's really weird. How do you take an x out of a -9? You could put a fraction, which is the equivalent of a decimal. Nobody does it that way. Okay? Once we get here, everything left over is a remainder. Okay? So the answer is this remainder -9. Okay? But does that really make sense? No. This equation went into that equation this many times with -9 left over. So there's another way to handle the remainder. Either you say 8 remainder 1, or you say 8 plus the remainder divided by the original divisor. So we could do 6 remainder -9, or we could say plus -9 over x plus 1. Now Alex is going to ask you both, not at the same time, but some problems will say state the remainder, and some problems will say just include the remainder in your answer. Okay? So let's do another one. Oh. Okay, now here's a disclaimer. It is very probable I'm going to change my numerator as we go, because I don't want to end up with a really, really difficult problem. So we'll start with this, and I might end up changing some of these. So we stick 2x minus 4 on the left. I don't know how long this is going to be. So I bring down the 4x to the third. What should go here? 2x squared. Does everybody understand that? Everybody's good? 2x squared, which allows me to put negative 8x squared down here. So I'm done with this one. Next one. This box and this box need to add to be negative 12. So negative 4x squared. I pull out a 2x, and I'm left with negative 2x. Is everybody good so far? Okay. Negative 2x times negative 4 is negative 8x. Oh, positive. Positive 8x. You guys wonder how I ever graduated college. Well, I graduated 3 times. That's how. So, I'm done with that. I have 8. I need 6. Subtract 2. Pull out a 2x. Negative 1 times negative 4 is 4. Did this go in evenly? No. There's a remainder. To create the remainder, I add a column. I have 4. I need negative 8. Negative 12. So either my answer is 2x squared minus 2x minus 1, remainder negative 12, or the other version is 2x squared minus 2x minus 1 plus negative 12 over 2x minus 4. Well, yes. However, the problem will tell you how it wants the solution to look. So in ALEKS, some of them will say, state the remainder at the end, and some of them will say, write the equation and include your remainder as part of the equation. But this right here is essentially the same thing as Jensen handing me 3 8-foot ropes and a 1-foot rope. That doesn't do what we need it to do. And this is really weird, but let me show you this. This graph here and this graph here are exactly the same. Exactly the same. Which is weird. But if this goes in evenly, right? So if I had this and those cancel, then this graph and this graph will look differently. How will they differ? The second one will be missing one of the roots. Does that make sense? The first one will have 3 roots, and the second one will be missing that one root that divided out. So what did we really do? Well, if we had 3 over 2, or 1 and 1/2, 3 does not go into 2, right? So basically, this is an improper fraction. Oh, I meant this graph here. Sorry. That graph and this graph are the same. This is the top-heavy fraction, and this is the mixed number. We'll head that direction. Right now I'm teaching you division, and then we'll use division to do things in the future. So all we're doing now is adding a tool to your toolbox, and I'll teach you what the tool is for later. But basically, if you have a remainder, you are switching from an improper fraction to a mixed number. Okay? And hopefully, if we had 24 over 6, 6 goes in evenly and we end up with 4. That's what we want to happen. But if it doesn't happen, so if it's like 24 over 5, oh, I really killed that. Huh, weird. 24 over 5, that is the same as 4 and 4/5. And those two fractions are equal. They just look different. Okay? Now, we didn't do everything in that second set. This one. So, look here. Do the division, quotient, remainder. Okay? Quotient, remainder. Oh. Number 3, you don't know how to do yet. So if it says the word synthetic division, just skip them for today. Quotient and remainder. Oh, it doesn't do any of them the other way. I was wrong. Sorry, guys. So you need to do 2.1, and you need to start 2.2 when you get finished. And we'll work more on that next time.